This next example I like because it does have some intuition behind it. The question is, if you have a cosine of 7t, sinusoidal steady state, what is its Fourier transform? So the intuition says that the Fourier transform explains where the energy is in the signal. You know that a cosine of 7t, all of its energy is at omega equals 7. How much energy is there? Well, if it's been running for all infinity of time, it has an infinite amount of energy. So you'd expect to see some of these Dirac delta functions, these impulses, at omega equals 7. Before we dive into it, though, I want to do a quick review of Euler's identity. Euler's identity says if you take this complex exponential, it has a real part, and that real part is cosine of omega. And it has an imaginary part, which is sine of omega. And so using a little bit of algebra, we can then solve for what cosine of omega is in terms of complex exponentials. And that is 1/2 times e to the j omega plus e to the minus j omega. Similarly, we can solve for sine of omega, which is equal to 1 over j2 e to the j omega minus e to the minus j omega. So as you're copying this down, don't forget that there's a j that appears here, and it's a minus that appears over there. Now one could naively put in the Fourier transform formula right here. Plug in that cosine in here. And you'd get a hot mess. This is a tough, even PowerPoint doesn't want to let me write it. This is a tough integral to evaluate. If you're a little bit smarter, you can substitute this cosine of 7t here for this cosine of omega. Just put in omega 7t. And you'll get in a bunch of exponentials, and maybe you can manipulate them around and do something like that. There's a smarter way to do it yet. Don't do this at all. Instead, just realize that because Euler says f of t is equal to 1/2, let's see, cosine of 7t, we'll plug in, every time I see omega, I'll write in 7t. And so we say that's equal to e to the j omega, not omega, but 7t, plus e to the minus j 7t. Because Euler says this, and because in the last example we derived these relationships, now we can just read it right off from this bottom one. We can say that, therefore, our f of omega has to be equal to, let's see, 2 pi times 1/2 gives us just pi. And the first will be an impulse at omega minus 7, and the second will be an impulse at omega plus 7. So if we were to graph that, we get two impulses at 7 and minus 7. This is versus omega. We are graphing our f of omega, and the values of these impulses are that they have areas of pi. And again, this makes intuitive sense that this cosine of 7t, all of its energy is focused exactly at 7 radians per second and at minus 7 radians per second. And now we've added a new line to our table, and that is that a cosine at a particular frequency has as a Fourier transform this pi times an impulse at both the positive and the negative frequencies.